Welcome back. Let's take a look at how we can graph parabolas that are given to us in standard form here. We've been asked to, and I've chosen this to include in the major part of our review, even though it's something that we don't often spend a lot of time on, graphing parabolas in grade 10, because when you know this trick about the standard form of parabolas, you will be able to visualize parabolas very quickly, and that's going to add on to your error checking tools, give you more information that you can use to crack problems and have fun in this course. I really enjoy these ideas. So let's take a look at our general parabola. This is y equals x squared. Of course, it has a vertex at 0, 0, and it's opening upwards. Its stretch factor is 1. If I were to take that a and make it -1, then it would be opening downwards. I have sliders here for the variables a, b, and c, and yeah, you can see those sliders down here. Now, let's keep a at 1. As we change a, you'll notice that the parabola gets pulled and pulled taller and taller. This is something that people learn to visualize in grade 10. And that's important. And then what's the influence of c? Right now, c is set to 0. And as I increase c, I notice that the y-intercept of the parabola increases. And as I decrease c, the y-intercept decreases. And the value of c here I set it to -5, and I notice that this parabola is crossing at -5. So the value of c is always the y-intercept of the parabola. A gives me the stretch factor. If I turn this into a negative parabola, it stretches down, and if I make it 10x squared minus 5, then it's lifted very, very high. But what about b? And we don't talk about b very much in our courses. So let's set a back to 1 and c back to 0, and let's take a look at what b does. Here b is 0. It's hard to see where b is in that graph. Let's take b and make it 1. Moved over and down. That's interesting. The y-intercept stayed the same, but it's now no longer the vertex. Okay. All right, let's see what happens if b is 2. We can move down and over again. Y-intercept is still the same. The stretch factor is still the same, but the vertex now came down here to -1, -1 when b became 2. What if we make b 10? Oh, the vertex keeps on going over and down. It's really hard to see what b is influencing. C, of course, the y-intercept has stayed the same. Let's take a look at, I'm going to add one more tool to help our visualization here. A y equals bx plus c. Oops, plus. There we go. So here is the line in black, y is equal to bx plus c. The value of b and c is going to change along with this parabola up here as I move the slider. So let's change the slider for b. As I move that slider, do you see what's happening there at the y-intercept with that line? When I have the line here, this is the parabola y is equal to x squared plus 3x plus 0. And this is the line y is equal to 3x. Notice that the slope of the line is 3, and the slope of the parabola as it crosses the y-axis is given by b. You see that there? If I zoom in, this line is parallel, in fact, it's tangent to the parabola at the point where it crosses the y-axis. Now, a parabola doesn't have a slope. A parabola has a constantly changing slope, and the rate that the slope of the parabola changes is given by a, is given by its stretch factor. But the y-intercept is a very interesting point of the parabola. The value of the y-intercept is given by c, and how slopey the parabola is when it crosses the y-axis is given by b. Let's take a look at a negative value of b, and we'll see that the parabola starts to slide down this slope on the other side. This is y is equal to x squared minus 2x. Notice that the vertex is down here at 1, -1, but that the y-intercept is still given by c. C is still 0, and I can change that. I can move it up, and the whole thing would move up, and the whole thing would move down. But the slope as it crosses the y-axis is given by b. That allows you to look at a parabola in standard form, and without converting it to factored form or vertex form, you can visualize it like that. So let's take a look at how we can use that to create a table of values here and graph this parabola. So in this case, I'm starting with my y is equal to ax squared plus bx plus c. I have this parabola as y is equal to negative x squared, so it's opening downwards with a stretch factor of 1. It has a slope of 14 as it crosses the y-axis, so it's rising as it crosses the y-axis. That tells me that its vertex is into the negative x's because it's rising, and its vertex is down there at minus 48. Sorry, it crosses the y-axis at minus 48. So this is what I visualize immediately. I know that it crosses way, way down there at minus 48 and that it's rising, but it's opening downwards, so its vertex is something like that. It might be up there in the second quadrant. It might be down here in the third quadrant. This is the first, second, third, fourth quadrant. I know that its vertex is going to be somewhere over there, and I know that it has roots because the problem told me it has roots. So let's go ahead and find those. So now what I'm going to do, even without doing any algebraic manipulations or anything, I can create a table of values right away. And because I know to look in the negative x region, I know what values for x I can choose to figure out where the vertex is, where the roots are. So let's go ahead and prepare a table of values. We're going to have our x's and our y's. And let's start with -3, -4, -5, -6, and see how we do. Okay? So I'm going to input those and process them. And so I'll do the first ones, and then I'll pause for you. So this is y is equal to negative, and I'm going to do -3 here, -3 squared plus 14 times -3 minus 48. And let's see what we get. We would have a -3 squared would give me -9. So that will be y is equal to, I've done this wrong. Oh my goodness. Ha! I'm not going to re-record the video. I'm going to embrace my mistake. This is a powerfully negative slope. Actually, this has a positive slope here. So my visualization is really off, and I often make these types of mistakes when I'm talking and speaking at the same time. So let's fix that. This has a powerfully positive slope, so its vertex is going to be in the positive x region, somewhere like that. Notice that the algebra showed me very quickly that I was going to have a mistake, and I want to find these types of points, the vertex and the roots, and I'm going to guess that I can find them somewhere in these positive x values. So let's try +3. Here we would have -3 squared, which would be -9, plus 14 times 3, which will be plus, what is that? 14 times 3 gives me 42, minus 48. So this is still well down here. This is the point 3, -15. So let's try the point 5. So I can substitute 5 in there for x. Minus 5x squared plus 14 times 5 minus 48. So this will be equal to minus 25 plus 14 times 5, which is 70, minus 48. Let's see what we have there. Minus 3. So now let's expand our table of values. Actually, 6 is a very interesting point. Let's take a look at 6. When I substitute in 6 for x, I will find one of the roots. -6 squared, -36. 14 times 6 is 74. Minus 48. -36 minus 48 oh, this is, sorry, 84. 14 times 6, yes, that's 84. So negative 36 minus 48 is negative 84. Y here is 0. So there, I found one of the roots. So let's put these points on and see what Desmos is showing us so far, or sorry, Delta Math is showing us so far. We had the points 5, negative 3, and 6, 0. 5, negative 3, 6, 0. So the parabola is coming up here. It started way, way down here at minus 48, and it was rising as it crossed the y-axis. I happen to know from step pattern that 7 is going to give us the vertex and 8 is going to give us the other root. So let's experiment with the values of y is 7 and y is 8. If I look at let's substitute 7 in there for x. This will give us the vertex. So negative 7 squared is negative 49 plus 14 times 7. 14 times 7 is the same thing as 2 times 7 times 7. So that's plus 98 minus 48. So minus 49 minus 48 is going to be minus 97. And that's 1 less than that. So that would give me y is equal to 1. There's the vertex. It's going to be the point where it rises and it's going to start coming down again. So this is the point, x is 7, y is 1. That's this vertex here. Now, I don't need to keep going and finding more points because the parabola is going to be symmetrical around that vertex. So I know that point and that point are also going to be on the parabola. And this is what the parabola looks like. They have decided to make a table of values. They started choosing values at 4, similar to us, and then they went all the way up to 10. Notice the symmetry around the vertex allows you to, once you found that vertex, or you found 2 points that are symmetrical around it, 8 and 6 in this case, you can map these y values down to the corresponding x values based on the symmetry of the parabola. So that is how we can visualize and work with parabolas that are in standard form without converting them to factored or vertex form.